Good morning on and all. Now we are going to discuss about the topic congestion control algorithms. Before going to the topic, let us know what is congestion and then discuss about the various congestion control algorithms. Let us take a real-time example. In our lab, if our total number of systems is 60, but we have 70 people in a class, if they are coming for a lab, then we are in need of extra space, and this is known as congestion. If the capacity, incoming capacity is more than the actual capacity, then it is known as congestion. In case of mobile networks or the mobile communication, congestion means we have two parties in our communication. One is the sender and one more is the receiver. If the rate of the packets which are being emitted by the sender into the communication channel or the tunnel is greater than the rate of the packets which are accepted by the receiver, then it is known as congestion. Many congestion control methods have been proposed. Of those, 4 are being widely used in real time. And how can the congestion be controlled? Can be controlled by using various mechanisms. Already we know about what is slow start, what is congestion avoidance, and what is fast transmission. There are totally 4 methods. First one is the TCP Tahoe, second one is the TCP New Rano, third one is TCP SAC. SAC means sequential acknowledgement, and then the last one is TCP VGAS. First, TCP Tahoe. This is being the widely used congestion control algorithms. In this TCP Tahoe, we have all the 3 methods which are being used for the improvement in the performance of TCP. First one is the slow start, and then the congestion avoidance, and last one is the free transmission and free recovery. Slow start. Generally, slow start occurs when there is a start or the initial phase of the TCP session. Suppose if the window size is 5 and the sender sends more than 5 packets, then congestion may occur. In this case, initially the tunnel goes into the slow start phase. In slow start phase, the size of the congestion window or the transmission window is being reduced to half of the existing size till the congestion is being overcome and the number of packets being transmitted and received is equal. After the slow start, we have the congestion avoidance. Before in slow start, the increase in the window size is exponential, which means doubling. Suppose initially the window size is 5 and there is no congestion for transmitting 5 packets. We are having the packets P1, P2, P3, P4 and P5. After transmitting each packet, we will be receiving the acknowledgement from the receiver. Once we receive acknowledgement for one packet, I mean P1, then the number of windows, or size of the windows is being doubled. Suppose if there is a congestion, then the size of the window is being halved to avoid the congestion and overcome the congestion. And the second phase is the congestion avoidance. In congestion avoidance, the size of the window is increased very slowly in order to avoid the congestion. Congestion avoidance, it takes place after the slow start in our TCP communication. Once the slow start stops, then the congestion avoidance starts. Here is the graph of the slow start entire communication. Initially, we will be having the slow start, which is starting at the initial phase or when the TCP communication starts after the slow start. And here in the congestion avoidance, we have the threshold. What is threshold? Threshold is the minimum capacity after which or above which there will be the congestion or any problem in communication. In congestion avoidance, we have the threshold, and later we will be going into the fast retransmission. In retransmission, the retransmission will occur if we have received 3 duplicate acknowledgements for a same packet. Suppose if you are transmitting the 5 packets, in case if there is 3 acknowledgement received, 3 duplicate acknowledgements being received for the same packet P1, then the fast retransmission algorithm is being evoked. Here the retransmission timer is not considered by the particular in this fast retransmission phase. Here if we receive 3 duplicate acknowledgements, then automatically the communication stops. I mean the packets are being stopped by the sender till the acknowledgement is received for the particular packet P1. After receiving the acknowledgement, then it will increase, then it will send the further packets. Here the size of the window will be increased or decreased by 3 times of the actual size of the window, because why do we increase or decrease the window size by 3? Because here the condition is if we receive 3 duplicate acknowledgements, then congestion occurs and fast retransmission recovery come into action. That's the reason why we increase or decrease the window size by 3. And next one is TCP new Reno. In new Reno we have the partial acknowledgement. What is my partial acknowledgement? Suppose we have 5 packets and all are transmitted at the same time, then the entire frame will be having a sequence number and each of the packet will be having a specific sequential number. Suppose if the sequence number of a particular segment is missed, then we will be having the partial acknowledgement from the receiver that this particular sequence number is missing, so that the sender will retransmit all the packets of the specific sequence number, which means the segment along with all the 5 packets will be retransmitted. Here after the before the retransmission, the window will go into the slow start phase, because once the congestion occurs, every time initially the slow start phase will come into action. In order to avoid the unnecessary data packet transmission during the fast recovery, we have the partial acknowledgements. In partial wait a minute. Here we have 2 types of windows. One is single window and multiple window. If there is one loss in a window, then slow start is enough. If there is multiple loss in a single window, then we should have fast retransmission and it will not be waiting for the timeout or the RTT confirmation. When multiple packets are lost, then the fast retransmission, fast recovery algorithm or the process come into the action. Normally multiple data packet loss is common in mobile networks, since there are multiple people communicating using the same base stations, and TCP Reno effectively handles the problem of multiple packet loss. And third one is SACK, TCP SACK. Yeah, here SACK means selective acknowledgement. As we told, the TCP new Reno don't wait for any timeout delay before retransmitting the packets. In case of this, if you are receiving duplicate acknowledgements 3 times for a same packet, then the entire segment is being retransmitted, which leads to the unnecessary retransmission of the data. In order to avoid this unnecessary retransmission of the data, we are going into the TCP SACK. What is my TCP SACK? It is the selective acknowledgement which enables the receiver to send the sequence number of the particular packet which have been missed alone to the sender. If the sender receives the partial acknowledgement, suppose we have a segment or a segment or a packet with 5 datas, and we are missing only the third data, then the receiver will send partial acknowledgement that the third data is alone missing, so that the sender will be capable of retransmitting the particular packet alone again and receive the acknowledgement that the third packet have been received. Advantage of this TSAK, selective acknowledgement, is that there is no waste of time or the packets which are being retransmitted by the sender. And when multiple packets are lost in a communication, then TCP SAC retransmits only the last packets. However, there are two problems involved in this particular method. Whereas first one is the sender need to list the sequence of the packets which are lost, and the calculation used for listing the sequence number is very tedious, and it will lead to the degradation of the performance of the communication between the sender and the receiver. And last one, is the TCP Vegas, which is the extension of the TCP Reno, which is our second approach. And in case of TCP Vegas, we'll be calculating the retransmission time, which is calculated by using the round trip time. The round trip time for each packet is the time between or the time of the sender sending the packet to the receiver and receiver sending acknowledgement that the specific packet have been received. It is known as the round trip time. Based on the round trip time, the retransmission time is being calculated. Suppose if there is a difference between the existing time when a duplicate acknowledgement is being received by the sender and the timestamp of the acknowledgement. The timestamp means the time at which the acknowledgement is being received. If suppose the time at which duplicate acknowledgement is received, the difference between the existing time of the duplicate acknowledgement and the timestamp of the acknowledgement, we are going to calculate it whether the difference is greater than the timeout value. If suppose the difference between these two values is greater than the timeout value, then we are going to resend the particular segment of packets. In the TCP Vegas, we'll be calculating the actual bandwidth and the available bandwidth. First, before calculating the actual bandwidth, we'll be knowing what is base RTT, base round trip time. It is considers the minimum round trip time of any communication. Generally, the first round trip time, which means the round trip time for the first packet, will be the minimum in any communication, and it is being considered for the calculation. After based on the available and also the actual bandwidths, we are going to calculate the time, and the actual sending time is calculated as the time between sending the packet and receiving the acknowledgement for the particular packet. And based on the available bandwidth, the congestion window size will be determined, so that the congestion window is being checked every time. So whether there is excess packets is being transmitted to the congestion window. Suppose if excess packets are being sent into the window, then congestion takes place and it will be automatically going to the slow start phase. Next. When suppose if the congestion window size is increased, the condition would be the available bandwidth will be greater than the actual bandwidth. Suppose if the actual bandwidth is greater than the available bandwidth, then the congestion window size will be decreased. Here, the TCP extension results in improved throughput, which means the last packets are being identified quickly. Suppose if the last packet is identified quickly, then it is going to be retransmitted. Only the specific packet will be retransmitted, and there is a significant computing complexity that we should consider during the specific congestion control algorithms, which will add to the complexity and also the degradation of the performance in the algorithm. Thank you.